Hi everyone. Thanks for coming to take some time to listen to my talk. And thank you to Obi for hosting me. My name is Sheu. I am a fourth year graduate at UCLA, and my thesis work will be on strong lens and cosmology. So, what is strong lens? Strong lensing occurs when a very massive object, such as a galaxy or galaxy cluster, lies between us, the observer, and a more distant galaxy, such as or just a more distant galaxy. And so the light from this distant galaxy gets bent in such a way that we see multiple images of that distant galaxy. So in this case here, this is a very famous lens quasar called RxJ 1131. And you see that there are 4 images of the same quasar around this lensing galaxy. So here's a simple 2D schematic of this concept. So here is the lensing galaxy, here is the source galaxy, and here is us, the observer. So these 2 hollow points are the images that we observe. And so say there is some sort of perturbation in the light curve of the source galaxy. When this occurs, we actually see this in both the images that we see, but with a certain time delay associated with them. And this is due to the light path taking different paths in order to reach us, and the light being affected by the lens, the gravity of the lens galaxy differently. And if you work through the math, you find that the time delays are inversely proportional to h0. And so theoretically, if you're able to accurately model the math profile for this lensing galaxy, you can recover h0 to a high precision. So let's talk about the systems we typically use to get these time delays. The usual scenarios are either lens supernovae or lens quasars. So so I've been involved in searching for both of these kinds of systems, but they both kind of have their pros and cons. For lens supernovae, their light curves are very well defined. Especially with type 1a supernovae, we know that their light curves are fairly standard. Peak and long, and then they dip off. And because of that, we get a very strong constraint on their time delay. That if we can't get their time delay. Because these events are fairly rare and they're transient, you have to get their time delays. And if you miss the mark, then you don't get time delays and you can't get cosmology for them. On the other hand, lens quasars are much more common, and they stay variable for a long period of time. The benefit of that is you can find a lens quasar and then go back to it, take their time delays, and then get h0 from them. But because their light curves are so much more stochastic, you have to observe them for a much longer time scale. So we already have, say, hundreds of lens quasar discoveries. So why haven't we settled on Hubble fiction yet? Why haven't we done a very accurate and precise late time measurement of the h0? And it all comes down to this concept called the mass sheet degeneracy. So say we have this kind of same schematic that I showed earlier, except now I introduce this infinitely thin mass sheet at the lens plane, defined by this parameter lambda. And say I also adjust the source galaxy such that I nudge it a little bit, and I adjust the amplitude of this transient event. Now, the images that we actually observe stay exactly the same. We observe the same time delays, we observe the same amplitudes, we observe the same locations of these images. However, the h0 that we recovered is now biased by this lambda parameter. So this is the main reason why we can't get, or we're struggling to get higher precision on our h0 measurements using lens quasars. And there are 2 places where we can kind of break this degeneracy. At the lens plane, if we better understand the math profile of these lensing galaxies, we can limit the manifestation of this mass sheet. And we can do this by getting kinematic data, specifically for better yet, eye view data, as well as we can use external population samples of elliptical galaxies in order to constrain this mass sheet at a population level. Additionally, we can also look at the source plane here and you can see when I was playing around with these parameters, I had to demagnify or like de-amplify the transient bit. And if we can actually fix the amplitude of this transient bit, this also breaks the matching degeneracy. And this is easily done with a standard camera such as the type 1A curve. I also want to talk about another different kind of cosmology that you can do outside of H0 with strong lenses. In this scenario, using multiple lenses, multiple source galaxies at different redshifts, you could actually constrain parameters such as omega m and w, the dark energy equation of state, independent of H0, i.e. independent of this matching degeneracy. And these kind of systems where you have multiple sources is very common with galaxy cluster lenses. So now I want to get into the main crux of my talk. I want to talk about these two lenses, A1433 quadruply lens quasar, and the Carousel Lens, which is a very relaxed galaxy cluster scale lens with multiple sources. So let's first talk about J1433. So this is a quadruply lens quasar discovered by Angelo in 2018. It has a source redshift around 2.7 and a lens redshift around 0.4. And we have a ton of data for this system. So let's start going into that. We have time delay measurements for this. You can see that these time delays are high cadence over the span of 4 years. And the benefit of that is that because it's the lens quasar and their light curves are very random, you have to map out and match these very large scale features within this time delay, within its light curve in order to get the time delay. And as you may remember, time delays are inversely proportional to H0. So the better we can get our constraints on these time delays, the better we can get H0 measurements. Here is our lens model that we built for the system using all of our HRT bands. I'm only showing the F160W band because it's the most informative in terms of its source light. And you can see that in our reconstruction, we can actually reconstruct the source very precisely at a pixel level in order to replicate the image as well as reconstruct the map profile of this lens. Additionally, we have around 10 hours of KCWI IFU data, which allows us to better constrain the kinematics of this lens galaxy. Here in the middle is the kinematic map of the velocity dispersion, and on the right is the line of sight velocity. So this gradient that you see here means that it's actually rotating. And so we use both of these maps in order to constrain its dynamic model in order to break its mass sheet degeneracy, in order to better inform ourselves of the underlying mass within the galaxy. Additionally, we used an external sample of around 60 elliptical galaxy lenses in order to further our knowledge of this mass sheet and at a population level in order to mitigate this mass sheet degeneracy even further. And all in all, using 6 of these kind of lens quasars, we're able to get a H0 measurement of 74.3% in our latest TV Cosmos 2025 output paper. Our ultimate goal is to get sub 1% in order to break this Hubble tension. And we hope to slowly make progress for that. And next year, we hope to add 4 more lenses to our sample. We also aim to integrate JWST high resolution imaging and spectroscopic data. And we also hope to minimize mass sheet degeneracy, the main source of our error, as much as possible using external samples as well. So moving on to the next lens that I want to talk about, the Carousel Lens. It's a very relaxed cluster scale lens with multiple sources. It was independently discovered by many groups, and the galaxy cluster redshift is around 0.5, with sources ranging from 1 to 1.7 in the image shown, in the HST image shown here. And so what makes this system so remarkable is how relaxed it is. You can see just from the image itself that it sports various textbook lensing configurations, from Einstein crosses to naked cusp to cusp and cores, cup and folds, things like that. So because of that, it seems to indicate that this system is very relaxed. We can use a very simple lens model in order to recreate the images and reconstruct the math model. So in this case, we only use two power laws, one centered at the galaxy cluster center, as well as this member galaxy. And from there, we're able to reconstruct the image to a high precision. And I want to emphasize that typically with cluster lenses, you either try to recreate or map, ensure that the image is mapped back to the same locations, or you try to recreate the image locations, or you try to fit a parametric kind of source model, source light profile in order to create the images. But what we do is basically do a pixel scale reconstruction of the source in order to replicate and capture all the fine detail within the images in order to build a better math model. Additionally, we have a ton of IFU data that we use to identify these different images and ensure that they map back to the same redshift, i.e. the same source. And with all this information, we do this kind of analysis that I talked about earlier, where we constrain W and omega n with just this one system. And we can see that with just this one system, we're able to achieve constraints similar to Camina 2022, which is using 5 clusters. And we attribute this just how relaxed the system is, how minimal we are using this, or how little degrees of freedom it has. And you can see on the right here is constraints in conjunction with CMP and Actinium Plus data. So here are the images that we showed, that we got within my paper and Rose et al. In prep. And since then, we've gotten more in-depth Muse IFU data, where we now find this many lens images, all the way up to redshifts of 4. And many of these images you don't even see in the HST. It's only visible in the Muse data. So we're trying to leverage all we can with this in-depth Muse data, and we're trying to refine our lens model even further by taking advantage the source plane or the source galaxy thematics as well. So you can see in the data profile here how this image is kind of pulsating as we vary through wave, and this indicates that the galaxy is actually rotating. And so we want to take that into account in our lens model now in order to further refine it and further build a more precise lens model. In addition, we also want to model these high redshift sources that's only visible in the Muse data. And when we fully leverage the Muse data, we hope to achieve constraints comparable to this yellow contour here. We also submitted a recent JDaWiz key proposal for this system, and we, if accepted, expect to find more than 15 different additional strong lens sources, all the way up to redshifts of 11, and which would also further constrain our constraints to this purple contour. We also hope to, with this many sources, the chances of finding a lens supernovae also increases as well, which would contribute to time delay measurement and H0 constraints now. So all in all, the system has a very high potential for constraining cosmology even further. So thank you for listening, and yeah.
Question. When you're talking about like the galaxy lenses, is there any like effect of the viewing angle, like the viewing angle of the galaxy? Does that play any effect in like what you're doing?
Yes. So we do take into account the like inclination and the viewing angle like that, because the shape intrinsically does carry. There's a bit of uncertainty that we have to account for when dealing with the orientation of the galaxy. Yes. So we do that, take that into account in our end product or H0 measurement. this kind of systematic set.
I just want to say that the beautiful picture, the beautiful monologue is, it did leave me without questions, but no, that's just stunning, really amazing.
Thank you.
How many more of these would be expected to be studied in the next 5 years, say?
5 more, do you mean?
Similarly nice
or
extensions?
Yeah, like, are these like super rare or will
so,
more be discovered by some, like,
Euclid or so.
I mean, this system is particularly relaxed, but in terms of, Gaussian cluster lenses, and maybe Seiji would know more about this as well, but he's doing like, there's further studies on a lot of these Gaussian clusters, and each of them, when using their lens model, can constrain cosmology on their own. So we hope to get better constraint on this kind of science with, I guess, overall more data. And while this system may be like remarkable in it being relaxed, there are a ton of Gaussian clusters yet to be discovered too.
I guess I did have a question. So I mean, if I just look at the image, it looks very obvious that there are these, I don't know, 4 heavy galaxies right in the middle. But so you don't have to worry about their individual contributions. Is the cluster hot gas so much more dominant that you just don't care, or?
Right. So what we found is that mainly it seems to be large profiles seem to be preferred. We assume that it's actually fitting for this dark matter profile,
Right.
and it would help if we have like X-ray data, which we hope to get soon. But in any case, your comment about like whether or not we map out these other galaxies do contribute to our systematic estimate, but uncertainties as well, which we account for in our final measurements.
Sorry, this might be a very nice question, I might misunderstand, but in the introduction part, you also showed the galaxy lensing cases, and you also mentioned about Hubble norms. But in my understanding, galaxy lensing, the time delay should be very small, so the Hubble constant can be constrained well in the galaxy lensing case.
So in the galaxy lensing case, so sorry, can you restate your question?
So in the some of the introduction slides, you showed this kind of galaxy lensing case, not cluster lensing. Then among the multiple images, the light distance is not so much different. So in my understanding, galaxy lensing might not be helpful to constrain the Hubble.
That's a fair point. Yeah. Typically, when we look at lens quasar at a galaxy scale, we're looking at time delays of at most 100, 200 days. Looking at cluster lenses, you get years, and because you get years, you get higher, less uncertainty, like percentage uncertainty on your time delay measurements, hence better constraints on each knot. I guess the drawback for using cluster lenses is that they're also much more complicated, and it's harder to get a better model. But these are trade-offs there. Definitely the time delays do contribute. There are much tighter constraints there.
Excellent. Thank you.